In this second video for section 4.2, we're going to look at another definition that's closely related to linear combinations. Again, we're going to start with a list of vectors. Let v1, v2, up through vn be vectors in some vector space V. Then we say these vectors span V if every vector in the vector space V is a linear combination of these vectors. So here's a very easy example. The matrix 1, 0, 0, 1, just the 2 by 2 identity matrix, spans the vector space of matrices of this form, so you have the same scalar in both entries of the diagonal, zeros everywhere else, because the k factors out, basically. Every vector of this form is equal to a constant times the 2 by 2 identity matrix. So that means this matrix spans the whole vector space. Let's work through a more theoretical kind of example to see how you can prove things involving these definitions. So we're going to suppose that we have two vectors, v1 and v2, that span a vector space V. If I have a constant that's not equal to 0, I want to show that k times v1 and v2 also span the vector space V. So what that means is I can replace the vector v with a scalar multiple of it, assuming I don't just multiply by 0. So let's work through what we need to do. We need to show that every vector in V is a linear combination of the new vector k times v1 and v2. So we need to pick a vector in V and show that V is a linear combination, lowercase v, is a linear combination of the two new vectors. Let's go back to what we know. Since v1 and v2, so I've dropped the k, the constant multiple, since these two vectors span the vector space V, then there are two scalars, c1 and c2, that satisfy this equation. So V is a linear combination of the two original vectors. But we can do a little bit of manipulation here, since k is not 0. What we can do is multiply by k over k. So this is the same as multiplying by 1. And what this allows me to do is collect and regroup. So I'm going to take this k and collect it with the v1, and then take the other two constants, c1 and 1 over k, and bring them to the front. So c times v1 is actually equal to c1 over k times kv1. So that means I can go back to this equation, this original linear combination, and replace the first term, c1 times v1, with this new expression to get a second equation. So the vector v is now a linear combination of kv1 and v2, because it's equal to this sum, a constant times kv1 plus a constant times v2. So that means we're done. We proved that our vector is a linear combination of the new vectors. Now let's talk about an important theorem. Again, we're going to have some list of vectors in a vector space. So v1, v2, up through vm are vectors in the vector space V. And this new set, U, is going to be the set of all linear combinations of my vectors. Then the theorem says that U is actually a subspace of V spanned by my vectors. So that means this is actually a vector space contained inside of V, and every vector in U can be written as a linear combination of my list of vectors. And there's a little bit of notation that goes along with this theorem that you should be aware of. So in the case of this theorem, we say that v1, v2 through vm generate U, and we write U is equal to the span of the set containing v1, v2 up through vm. So the reason why we use this terminology, this generate terminology, is that this theorem is often used as a way to build a new vector space or a new subspace living inside of our vector space. If we have any list of vectors that we might be interested in, we have this method, a very simple method, of building a new subspace that's actually spanned by our vectors. And I won't be proving this theorem in the video, but if you're interested in how to prove it, some of the theory behind it, then the proof is on page 226 in your textbook. And I do encourage you to read that. So now we're going to work through a little example using this theorem. I want to show that this vector, h of x equals 4x squared plus 3x minus 7. So our vectors in this problem are going to be polynomials again. I want to show that this is in the span of these other two polynomials. F of x equals 2x squared minus 5, and g of x equals x plus 1. So we have to think back to the definition to figure out what this means. I have to show that this vector is a member of this subspace. And in order to be in this subspace, that means you have to be a linear combination of the two given vectors. That's how this is defined. So what we need to show is that h of x, our vector, is a linear combination of f of x and g of x. So that means we need to set up an equation and try to solve this one. So 4x squared plus 3x minus 7, that's h of x, is equal to c1 times f of x plus c2 times g of x. So just as in the previous video, this translates into a system of equations, and it translates into this system. And the way that you get it is by looking at the coefficients on each side of the equation and realizing that the x squared coefficient on the left must match the x squared coefficient on the right, and so on. So the x coefficient needs to match, and then the constant as well. So over here, there's only one x squared term, a 2x squared times c1. So that gives us our first equation, 2c1 is equal to 4. And then for a second equation, we can look at the x terms, and there's only one over here, the c2 times x, and that has to match up with 3. That gives us a second equation. And then our third equation, this minus 7 needs to match up with c1 times minus 5 plus c2 times 1. And that gives us the third equation. And then we translate it into an augmented matrix. We translate the system and then go through the process of row reduction. And since this is just a couple steps, so I've written them out, we need to create a 1 in the upper left position first off. So divide through by 2 on the first row, and it gives us a new augmented matrix here. Now we need to clear out the first column, so we'll have to take row 3 and add 5 times row 1 to eliminate the minus 5. And after you do that, you now have this third augmented matrix. And the only thing left to do, since we already have 1s here and here, is to eliminate this 1 on the third row. And to do that, we'll just subtract row 2. And this is the final step of row reduction, since we have a reduced row echelon form matrix. And this translates into saying that C1 is equal to 2 and C2 is equal to 3. The solutions that's written down here. So going back to the original question, is H a member of the span of these two other vectors? The answer is yes, because it can be written as a linear combination of these two vectors.